Okay, so we're going to talk about some extensions of our simple linear model to intrinsically linear models. And in these examples, we are looking at models where we can transform the variables in order to get a model that has an equivalent linear expression. The first of our examples that we're going to look at is the reciprocal model. So the sort of typical linear regression model, simple linear regression, has an intercept and a slope coefficient and then an error term to predict our y value. Now, in the reciprocal model, what we're going to do is we're going to make a substitution and let our z variable, our dummy variable, be the reciprocal of our x variable. And that produces we can then construct a linear model on the z variable, and then by replacing it, we obtain a model that has x in the denominator, and we're multiplying the coefficient by the reciprocal of x, or we're dividing by x, rather than simply multiplying by the linear x. So this is a useful model. It's essentially, we're going to talk about the power model later, but this is a useful representation of an intrinsically linear model that's easy to achieve and does not impact the way that we express our error term. In principle, we could do this with any power of x, but when we do the calculations, the typical expression involves the reciprocal as a separate thing. We can do a similar transformation using a log model. If we think of our intrinsically linear model in terms of a dummy variable z, but z is representing the log of our x variable, then this becomes equivalent to a log model for x. And so again, we have an intercept, we have a coefficient of our log, and then we have an error term. And again, this has not affected the sort of error term at all, as long as the error is normally distributed with a mean of 0 and constant variance, then we have not changed anything about that expression. Now, things get a little more complicated when we transform the y variable. And there are two models that are considered intrinsically linear by transforming the y variable. One of them is the exponential model. Here, we're going to take the log of the y variable and then represent that as a linear model. And we can see how this is equivalent to an exponential model if we do a little bit of algebra. We raise e to the on both sides, and then that cancels the log. And then a little bit of algebra, we can split up our exponential. We can make a substitution, e to a constant is some other constant, we'll call it alpha. And so what we get is a constant times e to a constant times x. And then this is where our error term can potentially become complicated. And we'll say a little bit more about that as we go, after we look at the last of our intrinsically linear models. The power model is our fourth type, and that is obtained by transforming both x and y with a log transformation. So the log of y, the log of x, and we apply similar algebra to what we did with the exponential model. We raise both of these sides of our equation, e to the expression, to cancel our log on the y side. We do a little bit more math, and I'm missing my ln here. We do a little bit more math to simplify our expression. We make the same substitution for the constant that we did before. And we have one additional application that we have to do, which is to use log rules to bring the beta from outside the log inside the log. And then we can safely cancel the e in the log. And that leaves us with x to a constant power. And this power doesn't have to be 1. It can be anything. It can be negative. It can be positive. And then, of course, this one, too, we did all of this arithmetic without the error term in the expression, and now we add the error term back in. Now, these transformations, particularly the ones where we transform the y variable, can create potential problems, or these transformations can solve those problems. Now, when we transform the y variable, we're essentially also transforming the error term, because the y is the one, really, that's what the error term is the variability in y that's not explained by x. And so if we have non-constant variance, for instance, sometimes performing log transformations of the y variables can repair that non-constant variance problem, or at least improve it. But if we already have constant variance in our errors, then performing a log transformation on the y variables can produce can change our constant variance into a non-constant variance. So we have to be careful when we apply some of these transformations. And in the graphs in Excel, it's all sort of happening in the background, but we will look at how we can apply it directly in order to confirm the results and then to do further analysis with it. Now, all of these can be constructed, certainly the reciprocal model, not the reciprocal model, the power model, the log model, and the exponential model can all be constructed just on the scatter plot itself. Now, we do have to be a little bit careful when we transform a variable. The input can't be negative. And so sometimes, particularly when we're working with simulated data, we do have to be particularly careful that our simulations don't produce negative values, because that will sort of mess up with graphs. The model will not operate properly. But assuming that we have eliminated that potential problem, then we will have no problem making these transformations and finding our models from the scatter plots. But we will also show in Excel how to actually do the transformations ourselves, because then we're able to use more tools like the built-in functions for intercept and slope and correlation, and then also use the data analysis tool pack. None of which are designed to do anything other than linear models. And so if we want to confirm the results or get additional analysis based on what we find in the scatter plot, we will need to perform those transformations in order to get that. So now let's go over to Excel and look at some of the examples we've come up with. Now, because of the stated issues with taking logs of negative values, I've gone ahead and created the scatter plots and fixed models for each of our examples in order to make sure that the graphs work properly before we do the transformations. So I've created a reciprocal model, and if we click on the function, we can see we have a constant divided by the x value. I've added a constant here just to make sure, partly because that's part of the reciprocal model, but also just to make sure that I'm not getting down to 0, because you can see here I'm getting very close to negative values. And then I have a small error term here. Because these reciprocal values 1 over x, given the values that I have, I'm getting so close to 0, I need to keep my error terms relatively small so that they don't overwhelm the model or push us below 0 too frequently. But we can see we have a linear equation on the graph, which is not doing a very good job. It's only getting an r squared of 0.52. And this curved version is that reciprocal model. Now, when we estimate it in Excel with a power model, we are getting an exponent of approximately -1. That error term and the constant are sort of messing up our ability to calculate that directly from the graph. The reciprocal model specifically with that extra constant is easier to calculate from the after you do the transformation. But we can see that even with that potential problem, the R squared value is much higher than the R squared value for the linear graph. So this power model, approximately a reciprocal model, is doing a better job. And what we'll want to do when we create this is actually find that hopefully the reciprocal model itself, where we can perform the transformations manually, will do an even better job. This is the one that is sort of the most challenging to get from the graph. And so the other three are actually much easier because they are less specialized. So let's actually look at our log model. In the log model, we created, and I'll just show you the sort of continually updating version of it. I've built this data from a log model. So log of our X values times some constant plus a constant, and then our random error. And again, I had to keep it relatively small in order to get the correlation high enough that we could even tell the difference. If the errors are too large, sometimes they swamp the model. And again, we have an example here where we have a linear trend imposed on the data. This one I've fixed in place so we can continue to analyze it. The R squared value is higher than the R squared value if we apply the log model as opposed to the linear model. And then let's look at our exponential model. Again, the exponential model is another one that where we transform the Y values. And so we have to make sure that our Y values never go negative, or this will also fail to graph properly. And again, I copied and pasted these. If we go back and just look briefly at the exponential function, again, we have a constant times exponential times a constant times X. And then again, we have this additional error term. Let's go back. And so I've plotted again the linear model. We can see this is not a very good fit, even though we get a 0.73 correlation. When we impose the exponential model on our data, we actually get a 0.9989 fit. And so that's a much better fit to the data than we had previously. And then our last example is, again, the sort of general power model. If we go back and look at the function that I used to create it, that's the reciprocal one. It's a raised to a power other than an integer, although it can be an integer. The reciprocal model, specifically the X variable raised to -1, but this can be raised to a positive or negative value, either integer or decimal. It does not have an extra constant in addition. Typically, I added the constant here in order to ensure that it, again, didn't go to 0, because then the model will fail. But typically, it should not have any additional plus and minus signs. But we can see, that's why I use a small one. But we can see, again, I managed to keep it all positive. And we can see that the linear model doesn't do a bad job in this particular case. The power was only 1.5, which is almost 1. But the power model does a better job. Instead of getting 0.98, we get 0.996. And we can see our exponent here is about 1.7. Our original one was about 1.5, but we're getting similar values to what we would expect. Okay, so how do we create these models in the graph? I've pre-created them, but basically you create them the same way that you create a linear trend. And I will just recreate it. So you go into your add chart elements, you select your trend line and more options, and then you choose from among your options here. Now I'm going to double click on my curved line so that I get back into my power model, not the linear model. And in order to choose a different model other than the linear, you just have to choose from the menu here. So we could experiment in a typical graph. We don't necessarily know what model the problem is derived from. So we can experiment with different selections in order to choose the one that seems to fit best. We'll come back to polynomial models at another time, but remember those are combinations of integer powers and tend to be curvier, not a straight line and a single curve, but like possibly curvy, much curvier. So here we'll experiment with the intrinsically linear models. The exponential model does not do as well. So that's clearly not appropriate. The log model also does not do as well. That's not appropriate for this example, but the power model is the one that does do better for this particular model. And that's because it was created from a power model. So those are our three that we can do inside of the graphs. And again, as we've seen in previous linear regression models, we can display the R-squared value and display the equation on the graph. And again, I've done this for both the linear and the power model or the other nonlinear models in order for us to more easily compare them. But this is how we would construct them. Now, okay, so what we've done is we've created these models from the graph. Now, how do I create them without the graph? How do I get sort of more additional analysis? And so what we're going to do is we're going to look at these analyses specifically so that we can do those calculations. Now, for the reciprocal model, I'm going to use the second column of reciprocal values that I've calculated from my model in order to make sure that they're staying constant and preserved while I go through these transformations. So what I'm going to do is I'm just going to move my data a little bit further down. I'm going to copy it. And you can see these updated. I have a negative value in here, and that's why my reciprocal thing disappeared, but it'll come back as soon as that recalculates without any negative numbers. But we're going to work with these fixed values, which are already all positive. Now, the reciprocal function, we said the model was produced by taking the x values, these are the units in this case, the inputs, and taking the reciprocal of them to get the new transformation. So what I'm going to do is I'm going to say my new x is going to be 1 divided by my old x. So that was my z in my written explanation. And I'm going to do that for all of these. And then I'm going to copy my reciprocal model output over here. Now, the thing to keep in mind about this is that when we create a scatter plot, and it doesn't really matter when we do calculations so much, we can designate what's x, what's y. But if we want to create a scatter plot for this, then we're going to need to have what's going on the x-axis to appear to the right, to the left of our y values, and to the y values to appear to the right of our x values. Because if they don't appear in the sort of reading order, then they won't plot properly on our scatter plot. And so just to sort of confirm this transformation, what this should do is this should convert our graph to a linear model. Now let's go make our graph out of it. Again, now, because these are sequential, the Excel may sometimes try to create a line graph and not a scatter plot, and we don't want that. And we're going to impose a trend line. On the data. And then in order to do our comparison, since our graph above was not based on this initial data, we're going to also create a scattered plot of the original untransformed data. And then we're going to impose a trend line, in this case, a power model. Now, the thing to keep in mind here is, again, that our reciprocal model and our power model are not going to necessarily be perfect, because perfect matches in the reciprocal case, our power here is not -1. That plus constant is being incorporated into the simple expression to adjust that power, or you can't impose on the scatter plot the actual reciprocal model that we should have. But we see that this coefficient of X here and this multiplier out front are very similar to each other. And that's the kind of thing that we would actually expect if this was a representative of the same type of problem. The reciprocal, this is the thing that we're dividing by X. These should be, again, basically the same value. Now, again, these graphs look very different because we've transformed the X values, and the reciprocals for X are going to be actually in the reverse order from the original representation, because we're dividing. So these R squared values here in both of these examples, again, they're slightly different models because of the way that Excel creates their power function. But we can see that the R squared values are very similar, and this is a better fit to the data than the linear model. And I will just display those R squared values. You can see that the linear model in the original data is much worse than the 0.5 that we have for both the transformed data and the power model. Now, if we want then to do the additional calculations that come with regression, we can now do these from this analysis. We can calculate, for instance, the slope using the slope function, the known y's, comma, the known x's, and that will match what's in our again, the graph of our transformed data. The intercept we can get from, again, using the intercept function, known y's, x's, again, matches the graph, and we can get the correlation. And again, the correlation in this case can be either positive or negative, depending on the slope that we have out here. And Correl X, Y, the order doesn't matter for this one. And again, if we were to square this, we would get our R squared value. Or you could use the R squared function. Now, if we want to go further than this, then we can use the data analysis toolpath. Regression. The Y range. The X range. I'm going to put this at the bottom. And we're not going to worry about the residuals or the residual plots right at the moment. Again, the reciprocal function itself is not going to upset the constant variance problem that we have when done correctly, not from the graph, but from the transformation. And so here's our correlation right here and right here. Here's our R squared value that we got from the graph. Here's our coefficients right here. And then we have all of this additional information for our test statistics, our p-values, and our confidence intervals. So all of that additional analysis that we can do from the data analysis tool pack is available to us. We can't do it on the untransformed data because it will give us this linear version only. But if we do the transformations, then we can do the analysis on the transformed graphs, and then those will translate back into our intrinsically linear model. Now let's look at our log data. Now the log data will work a little bit more directly because we actually have a log model in Excel, and we don't have in the graph, and we don't have a reciprocal model directly in the graph. So again, I'm going to copy and paste these down here so that I can perform the transformations. And I'm going to call this new X because I'm only transforming the X's using the log. The log of 1 is 0. Now, another potential issue with the logs, anytime you take the log, you not only can't do negative numbers, you can't do 0. So if you have a X value, which is 0, this is not going to work. The one way that you can fix this is by adding a small constant to all of your X values, like 0.001 or something like that. That won't affect the X values in most cases, but it will pull the 0 far enough away from 0 that the log will still be able to function. And then the log outputs of our model. And now we make a graph of this, and this should match our other coefficients a little bit better. I am going to adjust my axes. And then I'm going to impose a trend line. And look, that is a nice linear trend now. And we display the equation on the graph. And let's look back at our previous model. And we can actually see the constant here of our new X is the same as the constant of our log model. The intercept is the same as the constant of our log model from before. And the R squared value here and here are identical. So performing the log transformation on X, we've now converted what was a nonlinear function into a linear function, linear in log X. And then now we can, as before, we can use our built-in formulas, or we can use our data analysis tool pack to do some additional analysis and get all of those additional transformations that we wanted. And these are my Y values for the log model. These are my X values for the log model. Blah, blah, blah. I think that's what I wanted. Output range. I don't want to put over there. I will put over here. And then go. And again, we'll just expand this a little bit so we can do our comparisons. And again, here's our coefficients. The coefficient of our log is the 2.25. The intercept is 15. Here is our correlation value, which again, we could calculate from the Correl function on our transform data. And here's our R-squared value that we got from the graph. Again, intrinsically linear model. And again, the thing to keep in mind is that when we reconstruct the equation, the new X is log X. Now let's look at the other ones. Now, again, for our exponential model, what we're going to have to deal with is we're going to have to transform the Y value, not the X value. So let's copy that down here just a little bit. Let's move my graph out of the way. So here, I'm not going to worry about moving I don't have to rearrange things because I'm not transforming X at all in this case. I'm only transforming Y. And so the left-right order will read okay. And I'm going to take the log of my Y value. Now, again, these Y values, they contain the errors and everything. And so we are technically also transforming our errors when we do this. And then we're going to create our new scatter plot. And we'll impose a trend line on this one. Linear version. And then compare this to our previous example. Now, again, we've transformed the errors as we've done this. So our correlation value, our R-squared values are not completely identical. But what we can think about is what are these powers doing to us? What do they mean? So recall that what we ended up with when we did our algebra, the coefficient of our X term became the power in our exponential function, the multiple of X. And so we can see here that this 0.2359 is the same as the 0.2359 that we have in our exponential function before. Now, what about this constant? That constant became the multiplier out front. Well, EXP of 1.1397, because remember, we raised everything to the power of E. That alpha is this multiplier right here. It's this number, this constant in our linear model raised to the E power, or to the power of E. All right, so we can see that these are now basically equivalent to each other. Again, give or take those error terms. what we're going to do is we're now going to create that data analysis tool pack result that gives us that additional information. And this time I am going to look at the residual graph because my errors have also been transformed. And so now I'm concerned that maybe my errors are going to have potential problems with them. So let's go into our tool pack. My X range is going to be these guys. And my Y range is going to be these guys. And I want my output not to appear over there. I want to appear over here. And I am going to check these. And then again, let's expand so we can read things. So there's our R squared, which was the same that we got from our scatter plot right there. Here's our coefficients that match our graph in both versions. Now, what we want to look at in particular is the residual graphs. And the residual graphs, sometimes when you do a bunch of these, they appear in weird places. See if I can figure out where they disappeared to. Oh, here it is. Here's our residual graph. Let's stick it right there. And you can see that, in fact, we did create a potential issue. Our errors look much bigger here than they do over here. So there's this pattern. The bounds look like. So this is because I created my original data with a constant variance. And so when you take the log or of the errors, then what you're going to get is a smaller value of, for larger outputs. So this is one of the potential problems that you can create when you do transformations. Now, if the reverse is true, if this was in our original data non-constant variance, then by doing the transformation on the Y variable, you can actually eliminate that maybe that if it's increasing, for instance, you can shrink it sort of in a non-linear way and then actually get good results. Now, these errors are not very large, and so we might want to argue that maybe this isn't such a big deal, but it is something to kind of keep in mind. Sometimes these transformations can create problems, and sometimes, but they may solve a problem, but create another problem in reverse. And sometimes you can actually use them to solve particular problems. But you do have, this is part of the reason why we do this analysis. And then finally, for the sake of completeness, we will do our power model as well. And for the power model, we actually have to transform both the X and the Y variables using logs. So we'll call this new X and new Y. And this is going to be the log of the X's. And this is going to be the log of the Y's. And then we will make our new scatter plot. And again, we really don't want a line graph. We want and this looks like a very nice straight line. Didn't want to do that. Let's try again. There we go. Why they always stick this in the middle of the graph, I really don't understand. Always ends up there. Again, let's look at 0.9964, 0.9664. Again, these are slightly, again, we've transformed the errors as well as transforming. So they're not completely identical, but we can look at the powers here. Here's our 1.72 is in the x to the power. That's where that ended up. And this constant, again, we can think of exp of our 0.0152, and that is our multiplier in front. That intercept became e to that number as the multiplier in front, and that is our 1.01. So again, then to get all of the other information, all of the other analysis, we're going to use our data analysis tool pack. And the Y range is these, and the X range is these, and the output range was going to put over here. And then let's see what happens to our residual graph. Oh, show it over here. We'll move it someplace where we can look at it. Maybe even make it bigger. All right, so again, because we did the transformation, our errors can become potentially weird. So we do see a little bit of a pattern here, which suggests that there's not necessarily a perfect fit. Again, some of that may have been because we were trying to create a model that didn't make the values negative, because power models with negativity is a problem. Also, because we transformed the Y variable, we changed the error sizes differently for different size values. And so again, we've created a potential concern that maybe wasn't there before. But compared to our graph, we can see that here is our squared value. This is the linear correlation. Here's our coefficients, which match what we got in our graph, except for the rounding. And so now we can do these other analyses. We can do our p-values. We can do all kinds of other things. And actually, in this particular analysis, we can actually see that the p-value here for our intercept is very, very high. And this is a sign that maybe we don't actually want an intercept at all. And so if we wanted to, we could go back and reconstruct this trend line. And we can set the intercept to be 0. And now it's actually gone even higher by eliminating that extra constant. And again, in the data analysis tool pack, we could redo this analysis by eliminating that intercept, we would also be able to then do our calculations for the resulting coefficients. And I'm just going to go ahead and just do that right now. I don't have to change anything except the constant is 0 and say where I want this to print. And I'm going to just print it out down here. And finally, we can actually see the intercept has been set to 0. And now all of our other statistics are looking good. Our R-squared value is higher. Our model test statistic is higher. Our p-value for our new X coefficient is even better. And let's see if we can find our residuals, our residual graph. I don't know where it went. Here it is. No, that's the one I was looking at before. Well, this is one of the downsides of having a whole bunch of these outputs all on the same sheet. You lose track of things. Sometimes those plots show up in weird places that you can't predict. Here it is. Let's bring it back over here. Make it a little bigger. Now it still has, let's zoom back in again. It still has the same problems that it had before. It has that same curve to it. But it's no different than this one. But what we've done is we've eliminated that constant. Okay, that was exciting.